Right, we're back. This is now episode 3 of Wavy Physics, and I'm going to be moving away from automotive somewhat and looking at planes. And I was inspired for this one recently by a situation I was in. I was at East London University, which is located right next to London City Airport. I was having a meeting with someone outside, and we found that we couldn't hear ourselves talk a lot of the time due to the planes taking off and landing. And it kind of drew me to the question, well, what if we got rid of these noisy gas turbine engines and we had electric motors powering the planes? I thought to myself, why haven't we seen that in commercial jet-sized planes at least? Would we see it in the future? What might it look like? So to get into this one, I had to do a bit of research into electric motors, batteries and that kind of thing, to put some numbers on it and give you a real answer of what we might expect. So first thing to consider is getting rid of the gas turbine engines. You're going to have to replace that with an electric motor. Certain criteria that is going to have to be met by those motors is peak power, peak thrust. So calculating the peak power made by current gas turbine engines on a couple of planes, taking examples, what would an equivalent electric motor look like, because you've obviously still got to generate the same amount of thrust. Then obviously you've got to replace the jet fuel with a battery pack. So what might that battery pack look like? What's it going to weigh? What kind of volume is it going to take up? Will you need more volume of battery than the amount of fuel space in a current plane? Then obviously hydrogen being an emerging technology, I wanted to look at what a hydrogen fuel cell plane would look like. So using the electrolysis of hydrogen to provide the electricity necessary for the electric motors. What would a hydrogen fuel cell plane look like? And again, so generally I'm just looking at the feasibility of battery electric powered flight and hydrogen electric powered flight in current commercial jets. So it was actually quite involved. I needed to do quite a lot of calculations, but I'm now in a position to give you an answer and an opinion on can it be done and whether we'll see it in the next few years. Let me take you through that now. So, as I was saying, to put some numbers on our question, will we see electric jet planes in the near future? The first thing we had to do is establish what size electric motors we need to generate the same amount of thrust that we would with a gas turbine. So, with a few calculations, I worked out peak power output during a takeoff situation of two pretty popular airplanes. So, we've got the Airbus A319, which is used for just short haul flights, London to Paris, London to Malaga, those kind of journeys, and also a longer haul plane, something like the 777-200 extended range. So with the A319 having a peak output of 105 kilonewtons per engine, that equals power in megawatts of 24.92. So that's using Jet A1, kerosene as the fuel. So moving on to the 777-200 ER, it's a much bigger plane, the engines are a lot bigger. Those generate 80.1 megawatts per engine. So if we were going to replace those with electric motors, they would have to have the same performance to generate the same amount of thrust. The plane is the same, all the other variables are kept constant, with just changing the electric motors. Looking for engines of the power, something of the order of the power that we need, what I found was big engines that are used in power stations. So there's an engine that generates 32 megawatts, but has a power to weight ratio of 0.1 kilowatts per kilogram, and that engine actually weighed 33 tons. To get an idea of where that sits with gas turbine engines, a 24 kilowatt engine found on an A319 weighs 2.5 tons with a power to weight ratio of 10 kilowatts per kilogram. And then similarly on the Boeing 777, the 81 kilowatt engine there weighed 8 tons. So an engine coming in at 33 tons isn't going to have any place on a jet. So what I did find was a smaller scale motor made by a company called MRAX. And that's only a 200 kilowatt electric motor, and it's actually designed for airplanes, so it's going to be small craft like Cessna's two-seater kind of airplanes. That MRAX engine has a peak power of 200 kilowatts with a power to weight ratio of 10 kilowatts per kilogram, which is actually around the range that you see in gas turbines. If the technology on the MRAX engine could be scaled up to the size necessary for the 777, keeping the same power to weight ratio, it would be a fair comparison. So it's hard to know without speaking to the electric motor manufacturers if you can scale up the technology like that. But what I did find is that there's a lot of work going into superconducting electric motors. and they have a predicted power to weight ratio of 40 to 80 kilowatts per kilogram. So to conclude that, currently the technology doesn't seem to be there, but in the future what I'm finding is that it should be attainable. So looking at batteries, an Airbus A319 can hold 19 tons of fuel. In terms of energy, using Jet A1 as the source, that comes in at 808,000 megajoules. So without taking into account the different efficiencies of gas turbines and electric motors, that 808,000 megajoules then converts to 224.5 megawatt hours of energy. So taking an efficiency of a gas turbine engine as 55%, which means 55% of the energy input goes towards useful work and 45% is wasted. That figure then becomes 123 megawatt hours of fuel is used to propel the plane. Further to that, looking at electric motors efficiency, they're roughly about 98%, so only 2% of the energy input is wasted in electric motors. They're much more efficient. That 123 megawatt hours then becomes around 126 megawatt hours with efficiency taken into account. And that ultimately means any battery we want to use with those electric motors on a jet or on the A319 is going to have to store 126 megawatt hours of energy. So using that figure and some current statistics from lithium ion batteries, what does 126 megawatt hours look like in a battery? And the answer to that is 503 tons and a volume of 202,000 litres. So with the fuel tank capacity size of an A319, 24,000 litres, 202,000 litres comes in at 8.51 times bigger than the fuel tank capacity of the A319. So to cut it short, 503 tons is completely unfeasible. The volume of the batteries needed is completely unfeasible as well. And it's a similar story for the 777-200ER. Total energy stored in those fuel tanks, 171,000 litres, 134 tons of fuel at peak capacity, 579,000 megajoules. So again, taking efficiencies into account, that figure then becomes 903 megawatt hours of energy needed to power electric motors to complete the full range of a 777-200ER. Doing the same sums, that comes in at just over 3,600 tons, and again, 8.5 times the capacity of the jet fuel tanks. So putting that into perspective with some common flight routes, flying from London Gatwick to Charles de Gaulle Airport in Paris on an A319, the battery size needed for that trip was 52 tons, and the volume of battery needed was 21,000 litres, which is just under the full capacity of the jet fuel tanks in the A319. That doesn't take into account reserve fuel, taxiing fuel. That is purely just the load required for the flight, and that trip is just under an hour. So with current battery technology, you're only going to be able to fly an A319 166 nautical miles, which isn't far at all. Now take into account a long haul flight, something like London Gatwick to John F. Kennedy Airport in New York, 3,000 nautical miles. And the battery needed for that trip was 1,580 tons, 637,000 litres, 3.72 times the capacity of the jet fuel tanks. So again, completely unfeasible. And the conclusion there is battery technology just isn't there. Even if electric motor technology is coming along, lithium-ion batteries at least are a long way off. With battery technology seeming pretty unviable as an energy source for powering commercial jets, I wanted to look at hydrogen. There's a lot of innovation and research going into that at the moment. It's kind of emerging in the automotive sector as something to be seriously considered. But I haven't heard any news of anyone looking at it for aerospace. Looking at some similar routes for an A319 and a 777, what would the weight of hydrogen look like? What the volume of hydrogen look like to complete those trips? And also, what would the fuel cell weight look like? Doing some similar calculations using a theoretical fuel cell efficiency of 83%. Hydrogen is a lot more dense than jet fuel in the energy it contains per kilogram, but looking at the energy it contains per volume, it's not quite what jet fuel levels are, even when it's compressed into a liquid form. Looking at the full range capacity, we'll start with the A319. So using the efficiencies of electric motors, etc., replace the 18,000 kilo capacity of jet fuel tanks in that A319, the equivalent weight of hydrogen needed is only 3,800 kilos. So from a pure weight point of view, it looks very attractive. But because you can't get the volumetric energy density of hydrogen quite the same as you can with a fossil-based fuel like kerosene, this is where it starts to struggle. The equivalent volume of hydrogen needed to replace the jet fuel tanks in a A319 is 64,000 litres, which is 2.7 times the capacity of the jet fuel tanks. Unless there's a way to compress hydrogen into a much smaller volume than we currently can in its liquid form, it's not quite going to reach the attractiveness of jet fuel. I know there's some research going into that. I know metal halides is proving to be a much more dense way to store hydrogen, but halides come with the additional weight which is a big penalty in aerospace. So looking again at the 777, the weight of hydrogen needed is 23,000 kilos, down from the 130,000 kilos of jet fuel. But again, the volume of hydrogen needed is 2.7 times the volume of jet fuel. So again, you're going to have a real problem storing it within the plane. It will start to encroach on the passenger compartments, which then means you can fit less passengers, which means you generate less revenue per flight. And so the airlines are really going to look at that in an unattractive way. Lastly, just a few words on fuel cell technology. At the moment, fuel cells are capable of producing about 1.5 kilowatts per kilogram. So looking at the 24 and 80 megawatt requirements of the A319 and 777 engines, that would then convert to 33 and 107 tons of fuel cells required. So that's a further consideration which really pushes hydrogen out of the equation as well. So wrapping up and concluding then, I should have closed that question as to why we don't see hydrogen electric and battery electric planes in commercial jet sizes at the moment, and why we're still using a relatively crude kerosene, and also some of the avenues that are currently being explored. There's loads of research and experimentation going on with these technologies, so I think in the coming years you're going to see a lot of advancements. So I hope you've enjoyed this episode. Get in touch with comments and questions. I'd love to answer them and communicate with you guys. I hope you've enjoyed it. Until next time.